In this video, I will introduce the concept of acceleration and introduce you to the kinematics equations. So first, let's define what acceleration is in words. So we know that velocity is the rate at which an object's position changes. But there is another rate of change that is also important in physics, and that is the rate at which an object's velocity changes, and that is acceleration. So acceleration is the rate. Remember, anytime you see the word rate, think of how quickly something happens. So it's the rate at which the velocity of an object changes. So the more quickly an object's velocity changes with time, the greater the object's acceleration. And the symbol that we're going to use for acceleration is A, and we're going to define it as the change in velocity of the object, which I'll label as delta V, divided by the amount of time it took for the object's velocity to change by that much. Now let's do an example with this equation here. So let's suppose we have a car, and let's say that the car starts from rest, which means that its initial velocity, v sub 0 or v naught, is 0 meters per second. And let's say that it speeds up to a final velocity, vf, that's the final velocity, of 60 miles per hour, and in meters per second, that's about 27 meters per second. And we can calculate the overall net change in velocity of the car, that's delta V. And the way we can do that is very similar to how we calculated the displacement of an object by taking the final position of the object and subtracting the initial position. But this time, since we're calculating the change in velocity, we'll do that as velocity final minus velocity initial. So in this case, the overall net change of velocity of the car would be 27 meters per second minus the initial velocity, which is 0 meters per second, which gives me an overall an overall change in velocity of 27 meters per second. Now, in order to calculate the acceleration of the car, I also have to give you one more piece of information. I have to tell you how long it took for the car to speed up to 27 meters per second. In other words, I have to give you the time interval, delta t. So let's say we're in a really fast car and I can reach 60 miles per hour from rest in 2.5 seconds. So keep in mind that 2.5 seconds is just a number that I came up with. You're not calculating that from anywhere. This is a given quantity. So using the above equation, we can calculate the acceleration rate of the car. And the way we're going to do that is we're going to take the change in velocity of the car and divide that change in velocity by the time interval delta t, which is just the amount of time it took for the car to change its velocity by 27 meters per second. So the numerator is 27 meters per second. We've already calculated the overall net change in velocity. And that change occurred over a time interval of 2.5 seconds. So I can go ahead and calculate that now. Okay, so the overall acceleration rate of the car is 10.8. And let's look at the units here. So in the numerator, I have the units meters per second. Okay, so I have meters per second in the numerator. And then I have a division sign, right? So we're dividing by 2.5 seconds, if you recall. And so the unit in the denominator is seconds. So I have meters per second over seconds, or I could say meters per second per second. That's another way of saying that. And so the unit for acceleration is meters per second per second. And since we have 2 seconds in the denominator, I could rewrite that unit as a meter per second times seconds. So we have 2 seconds in the denominator. We have a second times a second in the denominator. And you can treat units like variables. So just like in algebra where you have x times x is equal to x squared, seconds times seconds is seconds squared. So I could rewrite that as meters per second squared. And this is the unit for acceleration that we're going to use in physics. Now, it probably makes more sense to think of it as a meter per second, even though we usually don't write it that way. We usually write it as a meter per second squared. And the reason for that is because it kind of gives us an idea of what the acceleration is actually telling us. So for every 1 second, the car's velocity increases by 10.8 meters per second. So if we think of it in terms of meters per second, it makes a lot more sense versus meters per second squared. Except anytime you actually write the unit for acceleration, it's typically going to be meters per second squared. We could always go back to the representation meters per second to kind of get a feel for what the acceleration is telling us. So it's telling us that every second that elapses, the car's velocity is increasing by 10.8 meters per second. Okay, so now that we've defined acceleration, we can go ahead and introduce the so-called kinematics equations. And these are a set of equations that can only be used when the acceleration of an object is constant. So we're going to make an assumption here. And this is an assumption that we're going to make throughout the entire course. Since this is an algebra-based physics course, we're never going to deal with a situation where the acceleration changes with time. So the acceleration of an object in our class will always be constant. And that is the assumption that we're going to make, that acceleration is constant. It doesn't depend on time. That's the assumption that we're making. And if we make this assumption, we can write down 3 key equations that we're going to use in word problems in the upcoming lecture videos. So the first equation allows me to calculate the final velocity of an object, or the velocity of an object at some future time, based on a few things. Based on the initial velocity of the object, so how fast was the object moving at time is equal to 0 seconds, plus how quickly that object is accelerating, A. Remember, this is the acceleration rate, how quickly the object is accelerating, multiplied by the amount of seconds, the number of seconds that the object has been accelerating for. So in other words, this equation allows me to calculate the velocity of an object at some future time if I know how fast it's moving initially, that's the initial velocity v naught, if I know how fast it's accelerating, how quickly it's speeding up, and for how long it accelerates for. That's the t, time. Okay, and we'll do some examples with this equation in the upcoming videos. Here I'm only going to introduce the equations. Okay, the second kinematics equation allows me to calculate an object's displacement. How far does it travel in the x direction based on a few variables? So delta x, that's the displacement of an object in the x direction. How far does it travel in the x direction? I can calculate this for an object based on the object's acceleration. So I have a term 1/2 times acceleration times time squared plus the initial velocity v naught times time. So in other words, this kinematics equation allows me to calculate how far an object has traveled in the x direction if I know how quickly it's accelerating. Remember, A stands for acceleration, so I know how quickly it's speeding up. Time, t, how long has it been accelerating for? How fast was it moving initially? That's v naught, v sub 0. And t, remember we discussed that, that's time. How long has it been accelerating for? So in other words, I can calculate how far an object has traveled in the x direction, in other words, its x displacement, based on acceleration, so how quickly the object is speeding up, time, how long has it been accelerating for, and v naught, what was its initial velocity. Again, we'll show some examples using this equation coming up in the next lecture video. And the last of the 3 kinematics equations can actually be derived from the first 2. And We are going to empirically or experimentally derive the first two equations. We're not going to mathematically prove these two equations because it requires a little bit of calculus, but we will show how these equations come out from experiment, right? So we will do a lab where these equations actually come out and we can empirically verify them. But the third equation can actually be easily derived from the first two. So I'm going to go ahead and show you how to do that here. So I'm going to start with the first equation, and I'm going to square both sides. So I'm going to square the left side, and I'm going to square the right side. So I'm just squaring both sides. And if I square the right-hand side, that's equivalent to multiplying that quantity by itself, right? So if I square the quantity V naught plus AT, that's equivalent to doing V naught plus AT times quantity V naught plus AT, right? That's the same thing. And the reason I write it this way is because it's going to be now easier to FOIL this out and simplify. So on the left side, I have V final squared. On the right side, I have V naught times V naught, which is V naught squared, plus I can do a V naught times AT, so that's going to be V naught times AT. I also have an AT times V naught, which if I rearrange is the same thing. It's V naught times AT. And then I can do AT times AT, so that's just A squared T squared. Okay, now these two can combine. Those are the exact same term. So I could simplify this and write this as V final squared is equal to V initial squared plus 2 times V naught times AT plus A squared times T squared. So I'm going to focus my attention on these last two terms here. So let's rewrite the V final squared and the V initial squared. And what I'm going to do is I'm going to factor out a 2a out of these two terms here. Okay, so if I factor out a 2a, what's left in the first term? Well, we got rid of the 2, and it's now outside. And we got rid of the a, it's also outside. So what's left over? V naught times t. Okay, plus now the second term. We took out one of the a's, so now what's left? An a. We didn't take out any t's, so what's left over? T squared. And we took out a 2, but there was no 2 in front of the a squared t squared, so we have to get rid of that 2 by multiplying by a half. We can confirm that we haven't changed anything. We've just rewritten it slightly by just FOILing this out, by distributing the 2a to both of these terms. So I have 2a times v naught t, and indeed I get 2 v naught times at. That's our first term there. And if I do 2a times 1 half at squared, the 2 and the 1 half, when I multiply those two, I just get 1. So 2 times a half just gives me 1. A times a gives me a squared, which is what I had originally. And then I'm still left with the t squared in there. So I have a squared t squared for that second term. So it checks out. So what I've written is exactly the same thing. Now, why did I do this? What's the reasoning for that? Well, I already know what this is. That's our second kinematics equation. So if we look at the second kinematics equation, we have 1 half at squared, which we have here, that's our second term, plus v naught t, that's our first term here. Okay, so what we can do is we can just replace all of this with the displacement in the x direction, delta x. So we could write the third kinematics equation as v final squared is equal to v initial squared plus 2 times the acceleration times the displacement in the x direction. So this is our third kinematics equation. Now, this kinematics equation also allows me to calculate the velocity of an object at some future time, but instead of calculating that velocity at some future time in terms of time, like the first kinematics equation does, if you recall, the first kinematics equation allows me to calculate the final velocity, or the velocity at some future time of an object, based on time, right? T. So this equation, the third kinematics equation, allows me to calculate the velocity of an object at some future time. So in the future, that's why we call it v final, based on how far the object has traveled in the x direction. Not in terms of time. Notice that time isn't even in that equation. What's now in the equation is delta x, how far the object has traveled in the x direction. So based on how far an object has traveled in the x direction, in other words, its x displacement, I can now figure out its future velocity. But I also need to know how quickly it's accelerating. I need to know A, and I also need to know its initial velocity. How fast was it moving initially? Okay, so we have our three kinematics equations. We have v final equals v initial plus at. That's our first one. We have delta x is 1/2 at squared plus v naught t. That's our second one. We are going to verify these two equations experimentally in our next experiment. And then our third equation is v final squared is equal to v initial squared plus 2 times the acceleration times the displacement in the x direction. That's our third equation. Okay, so in the next few lecture videos, I'm going to show you how to apply these kinematics equations in word problems.